This is our first section in the vectors unit. We're doing V1. If you're following along on your note packet, we're going to start on page 2 of the new note packet for vectors. So, chapter V, all about vectors. We're going to talk about what vectors represent, how they're used, and then we're going to look at one case for vectors today. And then tomorrow we'll look at the second case that we have to be careful for. So, vector, we use vectors to represent speed, oftentimes force in physics, or distance. And we have to remember that vectors are defined by two things, a direction and a magnitude. The way we write or draw a vector is a tail. A vector always has a tail and a head. So when you're drawing your diagrams to represent vectors, you want to make sure that each vector has a tail and end without the arrow, and then a head and arrow end. I do take points off on diagrams if you don't have your vectors drawn correctly, because the head of the vector is going to help us represent direction of the vector as we draw them. A couple of things to note about vectors. A vector can be moved parallel to itself without changing its magnitude or direction. So we can pick vectors up and move them parallel to themselves, but we cannot shrink or grow vectors because those become new vectors. The magnitude changes when we shrink or grow a vector. We cannot rotate vectors either. Once we start changing the direction of the vector, then we have a new vector with a different direction. We will note vectors as we use them, as we write them, with a variable that has an arrow above it that indicates that variable represents a vector. We represent the magnitude of a vector using absolute values. Oftentimes you'll see me write it like this, with just single absolute value bars around it just to save time. But anytime we see a vector in absolute value, that means we're expressing the magnitude or the length of that vector rather than the vector itself. The length of the vector then represents its magnitude. Magnitude is completely separate from direction. So a vector needs those two pieces of information, a magnitude and a direction, both to be represented as a full vector. Okay, so magnitude is just a piece of it. Magnitude is the length of our vectors. So here are some examples of vectors with different lengths, and note that each of these vectors are being expressed with the absolute values because we're representing the magnitude or the length of those vectors. So we can take a vector, and if we switch the tail and head, what happens is we get the negative of that vector. So the magnitude is the same, and it just has a complete opposite direction, 180 degrees opposite direction. That's the negative vector. Equal vectors have both the same magnitude and direction. So on the left-hand side here of this slide, those are all representations of equal vectors. They're all parallel to one another. They've all been moved parallel to one another. All of their magnitudes are the same. So they have the same magnitude and direction, which means those are all equal. Not equal examples then are on the right-hand side. Either they have different directions, different magnitude, or both. In that case, those vectors are not equal. So we're going to focus on two methods. The next 2 days, we're going to focus on two methods for summing two vectors. There's actually one more. There's a third method that we'll talk about later on in this unit. But we're going to focus on the parallelogram method today. And then tomorrow we'll talk about the tail-to-head method. Now, it's very similar in the triangles unit to just identifying the case of the triangle first, right? Side, 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 angle, side, side. The same thing is going to be said for vectors. When we're asked to sum two vectors together, we want to identify the case first. That helps us figure out what method to use to sum the vectors. So I'm going to talk about when we would choose to use the parallelogram method or the parallelogram case versus the tail-to-head method, and then we'll actually focus on using the parallelogram method today. So the tail-to-head method, this is the first one that I will demo. This is not the one that we're going to use today, but we use the tail-to-head method when we're mapping a trip. So let's say we have this example that Johnny left home and he went to the library. So from home to the library means that's what the vector is going to look like. The tail is where we start, the head is where we end. And then from the library, he went to meet his girlfriend in the ice cream parlor. So then there's our second vector. we want to know what his net travel is. So his net travel then is the vector represented from where he began going to where his final location was. So this is our net travel, or the net distance traveled when we find the magnitude of that vector. So tail to head, we will use generally when we're mapping a trip, when we're trying to see where somebody went over the course of a couple of movements. Today what we're focusing on is the parallelogram method. So this is used whenever two vectors start in the same place. So whenever two vectors' tails are starting in the same location. The perfect example of this is when two people are trying to apply force on the same object. So imagine we have Maggie and Homer from The Simpsons. They're trying to remove a tree stump in their backyard. Homer is pulling with a force of 40 pounds. Remember, we can represent force using vectors. So Homer's pulling on that tree stump with a force of 40 pounds in one direction. Maggie's pulling with a force of 25 pounds in the other direction. So different magnitudes mean different lengths. They have different directions because they're pulling in different directions. And then the net force that they exert on this tree stump, now this is where it gets a little bit tricky. With the tail to head method, we just started our resultant vector where we started our trip, and the head was where we ended the trip. With this method, the parallelogram method, anytime we have two vectors that are starting in the same place, we have to use a parallelogram, thus the name parallelogram method. So I need to construct a parallelogram out of these two vectors, right, something like this. And then the resultant force, the net force that they are applying together on this tree stump, becomes the diagonal of that parallelogram. So that's what we're going to be focusing on today. One more thing to note about the parallelogram method, oftentimes, like in your textbook homework and things like that, you need to use the parallelogram method when you are given two vectors and the angle between them. So that's another case, like two vectors, they're going to start in the same position and you have the angle between them. That's going to kind of hopefully make you note that that's going to be the parallelogram method. All right, so this is what we are focusing on today. Imagine we have two vectors, A and B. We are given the magnitudes of those vectors, and we're given the angle between those vectors. So again, two magnitudes, angle between them means the tails are starting in the same location, which means we're using the parallelogram method. We're asked to find the magnitude of A plus B, something I'll call the magnitude of the resultant vector, the resultant vector being the sum of the two vectors that we have. Okay, note, we're not asking to find the direction yet. We only want the magnitude here. That's all I'm asking. So when we construct our diagrams, we are going to construct vectors A and B. We'll try to make the diagrams as accurate as possible. At least, like, if magnitude A is less than magnitude B, then vector A should be smaller than vector B. And then we'll try to, as accurately as possible, also represent the angle between them. And then we will be ready to set up for the parallelogram method. All right, we are on page 2 of the note packet. That's where we're starting today. I'm going to walk through example A, and then I will have you pause the video and try example B, and then I'll put the answer up, and then we'll get on to page 3. So here's the situation. We have vector A's magnitude is 17, vector B's magnitude is 43, and the angle between them, theta, is 29 degrees. And we want to find the sum of A plus B and then the difference of A minus B. We want to find the magnitude of both of those, and then also the angle that each of these resultant vectors make with vector A. That's where it gets a little bit complicated. We just want to make sure we have a relatively accurate diagram there so that we can find that angle eventually. Okay, so we're going to first start with the sum of A plus B. I'm going to try and do this with colors so you guys can follow along, but the first thing I'm going to do, I always really like to start with the longer vector. That's just a personal preference. And so what I'm going to do is I'm going to first sketch vector B, and I'm going to do that on the horizontal. So I know that the length of vector B, or the magnitude, is 43. Remember, I also need to make sure to include a tail and a head side of the vector. So my angle then is going to be over here. Okay, so I'm going to construct theta on that side. So that's what I'm going to do next. So I'm going to also construct vector A, And then the angle between vector A and B is 29 degrees. So I'm going to try and draw as accurate a diagram as possible for 29 degrees. And then also keep in mind that vector A is 17 in magnitude, which means it needs to be less than half the length of vector B if I want to draw it like relatively accurately. So I'm going to construct vector A to look like that. And again, the tails are starting in the same place because we have two vectors and the angle between them. And then the head of A is going to extend kind of upward now. So the magnitude of vector A is 17, and then the last thing we had here was the angle between these two vectors was 29 degrees. Okay, so the rule of the parallelogram method says we're going to next construct a parallelogram. All right, looks good enough. And I'm going to follow the rules of parallelograms. What I know about a parallelogram, just like rectangles, the opposite side lengths of a parallelogram are the same. And sometimes just that's just useful to have that information. And then one more thing about parallelograms is that the two angles at the base or the two angles at the top, they sum to 180 degrees. So 180 minus 29 is 151. This angle over here is 151 degrees. Right, and then this angle also would be 151 degrees. This angle over here would be 29. So I'm going to try and fill in as much information as I know, and then I'm going to draw the resultant vector, which means I'm going to draw the vector that represents A plus B. So this is where it gets really, really important that we have the right diagonal. So we use the parallelogram method to sum vectors because the diagonal of the parallelogram that we create with the two vectors is the sum of those two vectors. Now the question is, there's two diagonals in a parallelogram. You can go this way, you can go this way. We have to make sure that we pick the right diagonal. The diagonal that sums A plus B will always go through the angle that we were given. So we're going to go through that 29-degree angle, and this is our resultant vector. So that in red is the vector that represents A plus B. And because we're trying to find the length of that vector, we're finding the magnitude of A plus B. So there's our diagram. All right, so with that diagram then, we're asked to calculate the actual length of that vector, right? The magnitude of A plus B. So what do we know? Well, I'm going to draw half of that parallelogram, just kind of out here on the side. And I'm going to fill in the things that we were given. So that side over there was 17. That was 43. This is 151. And I'm just going to say that's R. Right? It stands for the resultant vector. We're trying to find side length R. We have side angle side of a triangle, which means I can use the law of cosines here. So A plus B squared is equal to, and in this case I'm using R, so that's what I'm going to keep. R squared is equal to 43 squared plus 17 squared minus 2 times 43 times 17 times the cosine of the angle between them, 151. Okay, don't forget to take the square root. So the magnitude of A plus B then, if I type all of this into my calculator, it's going to give us 58.45 when I round to 2 decimal places with 100 space. Okay, the next thing we're asked to do is to calculate alpha, which is the angle between A plus B and A. So the angle between A plus B, vector A plus B, and vector A. Remember, vector A was at 17 in magnitude. So A plus B is that red vector in our diagram above, and vector A is green. So the angle that we're trying to calculate here is alpha. That is not 29 degrees because this entire angle is 29 degrees. So we are trying to calculate alpha. If I were to go back to the diagram that I have up here in purple in that triangle, alpha is actually this angle up here. Okay. These two things are alternate interior angles. So that's actually what we're trying to find. So we can use different things. I'm going to note here, I now know this side of this triangle. So I have 3 sides of a triangle. We're trying to find alpha. We can use the law of cosines. You could also use the law of sines because you know it's not going to be an obtuse angle. We already have 151 degrees in the triangle. But I'm just going to set up the law of cosines here. So alpha is equal to the inverse cosine of 58.45 squared plus 17 squared minus 43 squared all over 2 times 58.45 times 17. And I just type that into my calculator, and we're going to get something like 20.89 degrees. There we go. Okay, so then for the second part of this problem, we were asked to find a minus b, the magnitude of that vector a minus b. So this is where it gets a little bit trickier. When we subtract vectors, we're going to approach it slightly differently. We know how to find the negative vector. Negative vector has just opposite direction. So in order to accurately diagram the vector negative b, I'm going to actually include vector b in my diagram as well, and then we will just move in the opposite direction to get negative b. This is where it gets just maybe a little bit more difficult. All right, so I have the diagram that we had originally for a plus b. We're going to go in, and now we're going to sketch a diagram that's going to represent a minus b. So I'm going to really quickly kind of make this a little bit bigger. Remember, I'm going to try and keep the colors the same. I graphed b in orange. So this was vector b. That was 43 in magnitude. And vector b I had constructed with its head to be on the right-hand side. And then vector a, that had a magnitude of 17, and remember that the angle between vector a and b was 29. So there's vector a, and then the angle between them was 29 degrees. But we are trying to find a minus b. Now a minus b, that's the same thing as saying a plus negative b. So what I'm going to do is I'm going to construct this negative b vector, which means that I'm going to look at my vector that represents b, and the negative vector is just the vector that goes in the opposite direction, has the same magnitude, so it should have the same length, same magnitude. So it's not negative 43, it's still 43 in magnitude, but that is our negative vector. It's just a different direction. So I'm not changing anything about the magnitude to get the negative vector, we just changed the direction. So then what happens is, if I construct a parallelogram with these two vectors, that negative b vector and my a vector still, it's going to look something like this. And then again, starting from the angle between these two vectors, the angle where the tails meet, to the opposite side of this parallelogram, that is the sum of these two vectors. Now, the sum of these two vectors, it was a plus negative b. That becomes our a minus b vector. Right? So it's a little bit tricky. Okay, well, we know something about this angle because this angle plus 29 degrees is 180. So this is 151. And then again, this is a parallelogram, which means those two inner angles in the corners, they add to 180, so this also then must be 29. I know that the opposite sides of parallelograms are equal to one another, so I can fill that in as well. And we're just asked to find the value of a minus b, the magnitude of the vector a minus b. So again, I'm not going to draw the triangle this time, but we can use the law of cosines to do that. A minus b squared is equal to 17 squared plus 43 squared minus 2 times 17 times 43 times the cosine of 29 degrees, because 29 degrees is now the angle opposite a minus b. That should give us, when I plug it into the calculator, 29.31. Don't forget to take the square root. And then beta, the angle between a minus b and a. Now this is where it gets a little bit harder to see maybe, but beta is going to be this angle in here, okay, between a minus b and vector a. So that's what we're trying to find. So again, just like I did with alpha, I'm going to use the law of cosine. So the inverse cosine of 17 squared plus 29.31 squared minus 43 squared, because that's what's opposite beta, over 2 times 17 times 29.31. Beta is equal to 134.70 when I plug it into a calculator. All right, you try the components of B, and then come back and check the answers after you're done. So pause the video, do B, and then come back. Okay, so the diagram for A plus B is at the top, and then the magnitude of A plus B is 52.56, and then alpha is 65.28. So there's the work. Go ahead and pause it if you'd like to kind of catch up. Check your answers, and then I'm going to do A minus B. All right. A minus B is here. The magnitude is 69.94, and beta on this one is 47.32 degrees. Okay, the last thing we're going to do is on page 3 of the note packet, and this is just practicing addition of vectors using the tail to head method. So we are given 4 vectors, A, B, C, and D, and they are drawn for us in the upper right-hand corner. And then we have a couple of problems, 6 to be exact, that are going to ask us to multiply those vectors by something we call a scalar to expand or contract the magnitude, and then sum or difference other vectors, right? Add or subtract them from other vectors. So the first thing I like to do when we're given problems like this is I actually just like to go over to where we've defined the 2 vectors, and I just kind of count. So like A has a base of 3, and then it goes up 2. B is a 2 by 2, and we want to make sure we maintain direction, but I just think that it's really quick to count all of these things and just help us draw them out later on. So D is 1, 2, 3, 4 units along the horizontal. All right, so when I go to draw 2A, so 2 is our scalar. It's just a constant that we're multiplying vector A by. What happens then is scalars don't change the direction of our vector, unless they're negative, I guess, but what they do is they help us change the magnitude. So what's going to happen when I draw 2A? If A is right 3 and up 2, then 2A is going to be right 6 and up 4. We're just going to double all of the things, all of the components of vector A. So if I start down here, 2A is going to be right 6, 1, 2, 3, 4, 5, 6, and up 4, 1, 2, 3, 4. So that is my vector 2A. Now, tail and head, really, really important here. The tail is down here where I started, and the head is where we ended. So that's vector 2A. And then negative B, so like minus B, right? So if B is down 2 and right 2, then negative B is going to be everything in the opposite direction. So positive B is down 2, right 2. Negative B is going to be up 2 and left 2. So we just want to make sure that we follow the directions of vectors. We'd be really, really careful about that. I need to move my 2A down a little bit so I can fit negative B. Okay, so again, vector B, down 2, right 2. So negative B, you can think about it as like opposite B, up 2 and left 2. So tail to head means I'm going to start negative B where 2A ended, and then we're going to just extend out to that place where we have the head of negative B. Okay, so tail to head means we put the tail of the second vector at the head of the first. And then this answer, 2A minus B, that is our resultant vector. So that's the vector drawn from our starting position to where we ended. So we're starting back at where we started 2A all the way to where we ended after we drew negative B. So that's our resultant vector. I can also write it here as 2A minus B. And that's it. We're just drawing these today. We're not actually finding anything. We'll do the calculations for the tail to head method in another lecture. All right, let's do one more example, and then you guys are going to just finish up the problems on page 3. Okay, so let's take a look at number 2. We have C minus 2D, so we're going to start by drawing C, and then we'll draw the negative 2D. So we're going to change direction for vector D, and then we're going to change its magnitude by multiplying all the components of D by 2. So vector C first. So vector C is right 1 and up 3, so pick a place to start. I'm going to color code this. I'll start down here. Okay, right 1 and up 3. This is where the head of vector C is going to be. Okay, so there's our vector C. So again, tail to head. The tail of negative 2D is going to be at the head of vector C. So negative 2D, we're doing two things to D. We're going to change its magnitude by multiplying all the components of D by 2, and then we're going to change its direction because of the negative sign. So D is 4 units long to the right, which means negative 2D is going to be 8 units long to the left. 1, 2, 3, 4, 5, 6, 7, 8. I'm going to move this so that I have a little bit more space to draw negative 2D. Okay. Straight 8 units to the left. 1, 2, 3, 4, 5, 6, 7, 8. There we go. Okay. So the tail of vector negative 2D is going to start at the head of vector C, and that is our vector that represents negative 2D. Now, our resultant vector then, the whole thing, C minus 2D, start where we started, and you're going to extend all the way to where we ended. And that is C minus 2D. All right, so do that for the other 4 problems that are left, and then you have a set of problems at the bottom, on the class calendar, and also at the bottom of page 3, and then a couple of bookwork problems as well. Email me if you have any questions.